Hello, I am Dr. Rashid Ahmed from the Department of Physics of Kohat University of Science and Technology. In the subject of Mathematical Methods of Physics 2 with the course code PHY 222, we are at the lecture number 17 and the topic is Legendre's Polynomials. In our previous lecture, we have learned about the Legendre Equation and its solution with the help of a power series, where we expanded the variable y in terms of x as a power series, and then we took the derivative of it and then a second derivative of it and substituted back to solve the Legendre equation. In today's lecture, I will show you two different methods of solving a Legendre equation and obtaining Legendre polynomials. So let's start with reviewing the Legendre equation again. We know that the Legendre equation is a second order linear differential equation of this type, where you see 1 minus x square multiplied with a y double prime, where y double prime is the second derivative minus of y with respect to x, and then we have minus 2xy prime. Y prime is the first derivative of y with respect to x, and then plus L into L plus 1 of y into y is equal to 0. Here this L is actually a constant, and at the end when we determine the solution of a Legendre equation, then we get every term in terms of this constant L. We know that this equation has numerous applications in various fields of physics like quantum mechanics, electromagnetism and heat. So we found its general solution in our previous lecture, which was a sum of two series, that is the A0 series. This is first series which we call A0 series. A0 is a coefficient, and then you see all the terms over here. The first term is a constant term, and then we have minus the second term, which you see involves L plus 1 into L and x square, and then involves other L minus 2L plus 3 and x4. It's like even series where you see the powers of x are even. Similarly, we had the odd series as well, where the coefficient was a1, and you see the first term is x and the second term is x cube, and here we have L minus 1 L plus 2 involving, and all other terms. For example, the next term is L minus 1 L plus 2 L minus 2 L plus 4. So this is kind of a power series of odd function over here. So we have two series, and our purpose is now to inspect it for different values of L. For example, we can start and with the even series, we can consider the even series like over here, and see that for L is equal to 0, when we choose L to be equal to 0, and also if x square is equal to 1, this series is divergent. That's what we see. That if we choose L to be 0, you can see that if we choose L to be 0 and x square to be equal to 1, what we get out of this series is of this form. Because we choose L is equal to 0, so from here you will get something. For example, you put L is equal to 0 here, L is equal to 0 here, you get minus 2, minus minus gets plus, and then 3 factorial is actually 3 multiplied by 2, so 3 cancels out, you get 1 over 3. And since you put x square is equal to 1, you can write this x cube as a x into x square, so x square is equal to 1, so you remain with the x, which at the end we take as a common. And similarly, if you put that into here, you make the similar simplification, that this L is 0, this is 0, this is 0, and this is 0. What you get, what remains upstairs there is 4, 3, 2 and 1, while 5 factorial is also 5, 4, 2, 3 into 1 multiplied. So up till 4 we get all terms cancelled and we just remain with the 5, and since we get two negative signs, so this is a plus sign, so we get 1 over 5. But the problem is with this series, if you test it with different methods, for example integral test or ratio test, whatever test you do for this series is divergent. So we see that in Legendre equation, when we have two series, so for our choice L is equal to 0 and x square is equal to 1, the series actually diverges. But what happens with the A naught series? Let's go there and check it. If we go towards A naught series, then what we get is y is equal to A naught, because it's a constant term, and since L is equal to 0 and it multiplies with all other terms over there, so therefore this series gives us what is that rest of the terms contain L and hence are 0. So therefore this series gives us y is equal to A naught. So it terminates just after first term. So if you go back and check the L naught series, you see L multiplied with the first term, L multiplied with everything. So if you put L is equal to 0, this term goes away, this term goes away, every term goes away because it contains L. So you have seen for L is equal to 0, when we chose, that this series actually terminates, the A naught series terminates after the first term, because first term does not contain L, therefore it is not 0. Otherwise all other terms just go to 0. So this goes to 0, this goes to 0, everything is 0 over here. But in here what we get, that this series is divergent. So part of so one series is divergent for L is equal to 0 and x square is equal to 1, but the other series is actually terminated after first term. That's very interesting. So you see over here that A naught series gives us y is equal to A naught for L is equal to 0, since rest of the terms contain L and hence are 0. So what happens, this is the first result we have seen. Let's see if this continues. We will again set some other cases. Let's say now do for L is equal to 1, and we did for L is equal to 0, now we do it for L is equal to 1. What happens when L is equal to 1? Then now A naught series is divergent at x square is equal to 1. But A1 series gives us y is equal to A1x. So if we look at back here, we go back over here. If we choose L is equal to 1, so what you see, if you choose L is equal to 1, so A1 series got L minus 1 in every term over here. So if you choose L is equal to 1, this is 1 minus 1 0, so this term goes away. This 1 minus 1 0, this term goes away, and so on. So now this series terminates at the first term and all other terms equal to 0, and this gives us y is equal to A1x. On the other hand, if we put L is equal to 1 over here, what we will get, we will get upstairs 2, so 2 factorial goes away, and so we will get minus 1 over here, and here we will get 2 and minus 1 and a plus 2, and so this 3 this cancels out, and you get as a series which actually, if you test it, is divergent. So again we have seen that for L is equal to 1 case, as it is here, the A naught series is actually divergent at x square is equal to 1, but A1 series gives us y is equal to A1x, and rest of the terms, since they contain L minus 1 and hence they are 0. So it seems like that it is a general thing that whenever we have one series, then whenever we choose the value of L1 and some value of x square, then one of the series goes away, terminates after one term or two term or after few terms, and the second series is actually a divergent series. So one terminates at something and some terms after some terms, and second series actually is a divergent one. And this is the whole story. We can check it. This is the whole story, that every time we does this, it happens to the Legendre series. So from this we can get a general result for Legendre polynomial, that one series is divergent at x is equal to x square is equal to 1, and another series gives a polynomial solution. So this is sort of our general result, that one series diverges and the other series gives us a polynomial result. And so Before moving on and finding out a general expression for polynomials, which we call Legendre polynomial, there is another thing which we have to tackle is the negative integral values. So what about negative integral values? That if I take L is equal to minus 1, since we have I have shown you for L is equal to 0 and L is equal to 1, but what happens if I take L is equal to, let's say, minus 1 or let's say minus 2, what happens over here? So in this case, in Legendre polynomials case, the negative integral values give results already obtained for positive L. So if you try L is equal to negative of something, for example minus 1 or minus 2, what you will find out that the results come out will be exactly equal to some of the positive values. So therefore we need not to calculate negative values. They are not really required because their results are already contained in there. So for example, as I have given an example over here as well, for example for L is equal to minus 2, if you calculate, it gives results y is equal to a1x in the a1 series, and which is the same as for L is equal to 1 in the a1 series. You have seen, and a0 series diverges. So if we take L is equal to minus 2, that is a negative integer, so what happens that the a0 series diverges and a1 series terminates after the first term, and this first term is actually exactly the term we got from L is equal to 1 case. So it is just the same. So therefore we can easily neglect the negative integral values for the Legendre polynomial. So we restrict only to non-negative values, which means that we don't need negative values. We can restrict ourselves only to positive values because negative values just give the results exactly same as we have in the positive values. Okay, so far so good. We have considered, we have obtained the general result of solving the Legendre equation, and we got two series there. We choose some value of our L and some x square is equal to 1, and we get this general result. So each solution contains an arbitrary constant. We know this, either a0 or a1. So we have an arbitrary constant involved in each and every solution. So for example, for L is equal to 0, this gives us y is equal to a0. If you remember, this was the case when we have taken L is equal to 0, our arbitrary constant is a0, and for L is equal to 1, our arbitrary constant is actually a1x. So the general result, another general result is that every solution which we do for any value of L integer value, we get some arbitrary constant is involved. For example, L is equal to 0, we involve a0, and L is equal to 1, we got a1. So then we are now ready to write a Legendre polynomial, because we have already actually derived some of them. For example, if value of a0 or a1 is selected so that y is equal to 1 when x is equal to 1. For example, now we choose, we say that if we choose the value of a0 and a1 in such a way that we get, when we put x is equal to 1, we also get y is equal to 1. So the resulting polynomial is then called a Legendre polynomial. So this is a condition, sort of condition for the Legendre polynomial. That is when we set y is equal to 1 and x is equal to 1, then our resulting polynomial is actually called Legendre polynomial. So here I will give you some examples, first few values for the Legendre polynomial. For example, this is the p0 x. When we set in all these conditions, we get p0 x is equal to 1. So this we got the 0th order polynomial or Legendre polynomial. Then p1 is the next Legendre polynomial, that is equal to x, and the second one p2 is equal to 1 over 2 3x square minus 1. So in this way you can calculate all the Legendre polynomials involved in the Legendre equation, the solution of the Legendre equation. These are just the first few 1, 2 and 3 terms, and you can easily calculate all other Legendre polynomial. For example, let's look at the first one, p naught x is equal to 1. So what we are saying, then if value of a naught or a1 is selected, so if we select a naught is equal to 1, so what was our solution? If you remember, y was equal to a naught. So if we set a naught is equal to 1 and x is also set to equal to 1, so if I set x equal to 1 and a naught and a1 all equal to 1, so what we will get, see, if I set a naught is equal to 1, so I have y is equal to 1, and if I have y is equal to 1 in this side, that it means that if a1 if x is equal to 1, then a1 is also equal to 1. So our first Legendre polynomial, the first solution was y is equal to a naught. Since we set a naught is equal to 1, so therefore this is our first solution. And similarly, if we in the second solution p1x, if you do the same thing again, then you see that our p1x is equal to x, and this is the p2 value. So these were the first few values for our Legendre polynomials, and in similar way you can calculate other polynomials as well, higher order polynomials. Now the next thing is about the eigenvalues and eigenfunctions character of a Legendre polynomial. We know that the eigenvalue and eigenfunction problem, since we know that the values of L we can choose L is equal to 0, 1, 2, 3. So these we term it as eigenvalues. So and then the corresponding solutions PL are called eigenfunctions. So if this constant L which gets involved into the Legendre equation and Legendre polynomial, if the values of L are these one, we call them eigenvalues, and their corresponding solutions PL are called eigenfunctions. In a moment I show you that how we can say that these are eigenvalues and these are eigenfunctions. This you can see from eigenvalue and eigenfunction problem. You remember that what is the eigenvalue and eigenfunction problem? Eigenvalue is problem or eigenfunction problem is like this, that if you have any function and this m is some operator, and this m operator is acting actually on this function, it could be a wave function as well, but any kind of function. And what happens, and this m can be a matrix as well, just multiplying it over here, or this m is just an operator. So when this m acts on r, we get the r back. This r is on the right hand side, multiplied with some constant. This constant is actually called the eigenvalue. So this is the eigenvalue, and this r is over here is an eigenfunction. This is called the eigenvalue or eigenfunction problem, where you see that we act with certain operator or matrix on a function, and we get back the function multiplied by with some constant value, and this constant value we term as eigenvalue, and this function is termed as a eigenfunction. Okay, so let's see that our Legendre polynomial is actually the same thing. See, in Legendre case, Legendre polynomial case, what we have done, that we had a function y, and this f of d, there was some function f of d, and when we sort of acted like on this function y of x with the f of d, d was a derivative, and what we got is L into L plus 1 into y of x. So it's just similar to the eigenvalue problem. We are getting a y of x as an eigenfunction back, and this L into L plus 1 is the value of L is actually the eigenvalue, and this f of d is actually playing the role of operator or a matrix which acts on this function and bring us back the function multiplied with some constants, which we called eigenvalues. So therefore, by this analogy, we can say that the Legendre polynomials, which are actually the solutions, are eigenfunctions, because this y's are actually Legendre polynomials. So these are actually the eigenfunctions, and these L's are L plays the role of eigenvalue. Okay, so with this we turn now to our next point or next topic in this lecture, and that is Regis formula. And Regis formula is actually is another solution to the Legendre equation. And excuse me, let's see that how Regis formula gives the solution of the Legendre equation. So this P of PL of x is a Legendre polynomial, as you know, and this is in this form is actually a Regis formula. And Regis formula, we now prove that actually gives the Legendre equation. So this is actually another way to solve Legendre equation, this Regis formula. And let's assume that v, some variable, is equal to x square minus 1 raised to power n. Okay, so this is we start with this assumption that we have some variable v which is equal to x square minus 1 and raised to power l. And then what we do is we find out the derivative of this function v with respect to x. Okay, that's not a difficult thing. In a moment I will explain to you how to find the derivative of v with respect to x, and then we multiply it with x square minus 1. So we got a function v, and we find out its first derivative, that is dv by dx, and then we multiply it with the x square minus 1. And what we obtain over here is this thing, that is x square minus 1 into dv by dx is equal to x square minus 1 into l into x square minus 1 raised to power l minus 1, so 2x. And if you simplify this, what you will get is 2l xv. So what we have done here, that we have found the dv by dx and multiplied on both sides with x square minus 1, and after this multiplication we have made a simplification, and from this simplification what we got is 2l xv. And if we differentiate this whole thing l plus 1 times, and l plus after the differentiation for l plus 1 times of this, like using a power rule or Leibniz rule, what you will see that if you differentiate each and every term, you will get x square minus 1 and this term into l plus 1, l plus 1 into this term, and l plus 1. So this all terms actually coming from differentiating this l plus 1 times. So you know, for example, if you differentiate this for the first time, what you will get from here from the product rule, and if you differentiate the result again and again and again up till l plus 1 times, so at the end you see this power actually coming for the l plus 1 time derivative. We have taken l plus 1 time derivative of this because it comes from the product rule again and again, and this is the result. So we can simplify this whole result into something like this. We can collect the same terms, and what we get after the simplification, this thing. And if you look at it carefully, and if you say that this thing is actually y, so this will be then y double prime, and this will be y prime, and this is y. So if you look at this and multiplied by 1 minus x square actually, and this is multiplied 2x, and this is l into l plus 1. So you see this is actually a Legendre equation. So what you have seen that is in then that Regis formula we have used, and we have solved it, and what we get is a Legendre equation. And these are the few references which you might want to look. And at the end, I would like to give you the summary of today's lecture. So in today's lecture, what we have done is derived a very important polynomials called Legendre polynomials, which are solution to the Legendre equation. And what we have done is a very simple choice of L and x square. And as we know that in the solution of Legendre equation, we have two series, that power series, one is even and one is odd, and we have two constants there, a0 and a1. We say that one is the a0 series and other is a1 series. So we actually chose the value of L is equal to 0 in the first case, and x square is equal to 1, and we have seen that for that case one of the series was divergent, that is a one series, and the other was terminating after the first term. And when we chose L is equal to 1 and x square is equal to 1, we seen that the other series was divergent, and the first one was terminating after the first term. By this way we found out the general formula, and after that formula we found out the Legendre polynomials. We also talked about the non-negative integral values of L, and we seen that they are actually already contained in the positive values. And at the end we went on to show that Regis formula for the solution of the Legendre equation. I hope you have got the idea of Legendre polynomials. With this, I thank you all.